So I left you off last lecture telling you that the root mean square current is the maximum current over square root 2, right, for sinusoidal wave. So this follows very simply for the voltage, because both current and voltage are in phase. Then for average power, we can simply do this. Remember, last lecture I left you off with average power is the mean square current times R. The mean square current is just the root mean square current squared. So the root mean square current is here, I naught over square root 2 squared times R. So you get I naught squared times R on the numerator. Square root 2 squared is just 2. So what you end up with, very interestingly, is that the average power for an AC current, right, is the half of the maximum. It's the half of the maximum. Right, and you get this. Okay? And this is very peculiar only to sinusoidal waves. If you see a square wave, can you write this down? If you see a square wave, can you write this down? Which is what I've done previously for you in page 7 and page 8. Can you write this down? Answer is? That's right, cannot, huh? So you must remember this. Right, moving on. Example number 4. The voltage of electrical power that we use daily from the electrical mains is 240 volts. How many of you know there's 240 volts from our mains? How many of you? Raise your hand. Okay. How many of you know that 240 volts in the mains is actually a root mean square current? Wow, good. Some of you know. Very good. How do you all know that? The boys at the back, how do you all know that? Secondary school? Yes, I'm looking at you, yes. Huh? Oh, you surf the internet. Oh, well done. I didn't know, when I was your age and I was after my O level, I know 240. But I didn't know it's a root mean square current. No, it's only until my JC then I think my lecturer said lah, but maybe I wasn't listening. But yes, I only knew it then. Okay. So what happens? They asked me to find the maximum peak voltage, so it's actually 340 volts. That means if something or someone were to get electrocuted, what is running through is not 240 volts. At times, it can go as high as 340 volts. That's a terrible thought. Right? That's a terrible thought. Next, they ask you to find the root mean square current for a kettle with a power rating of 1000. No problem. Right? So the power rating they have, if you look at your household appliance, your kettle, your refrigerator, your radio, right? If you still have those lousy ones, old ones like what I have, radios are around 60 watts, right? I actually remember when I go to a supermarket, electrical appliance store, they were selling a 60-watt radio for $100. Then the 120 watts one, they're selling like triple the price. Then I was like, wow, the one that is 300 watts would be better. But now that I know, I just know that the difference is that it consumes more electricity, which may not necessarily mean it's a louder sound or better quality, right? So it consumes more power doesn't mean it's better, huh? Right. Anyway, so back to this. Since you know that this rating is the average power, you can very quickly use and sub it in. Right? And since you also know the VRMS, sub it in, you can find the RMS. Very, very easy. Okay. So I say again, the learning point in this example is to know what power rating means. Okay, what power rating means. Power rating for any object that uses AC, that power rating is average power, not any other powers. Okay. Next, we have this. Tourist takes an electrical water heater designed to operate with 110 volts electricity to Singapore. No idea why. He will do that because you can, if you go to a hotel, there's always a heater, but never mind. Maybe he likes his own water heater. the water becomes cleaner after that maybe. He plugs it into a 240 volts outlet. Boom, and the heater breaks down. No, this is a real life story. This example, right, I didn't put in because it was there. I didn't put in just because it was there. Because it happened in my real life, you know. Few years back, there was a haze, very, very bad. You remember, the haze was very, very bad. And if you go to buy air purifiers, the machine ones, they were all sold out. Remember that? Yeah. So my cousin, he's very techy. So he said, okay, let me buy it from US. He buys online very often. So he went online and he bought it. He shipped it in from the US. After a few days wait, he said, okay, yay, finally you can breathe fresh air. He took it, he plugged it into a socket, boom. Right? It exploded. The sound was louder, boom, very loud. And then the room, which was already hazy, now has a fried electrical smell, the plastic, the metal smell come out. Right? So the air became worse. So why? Why? Because he bought it from the US, he bought it from Amazon. It was designed for 110 volts. Right? Designed for 110 volts. So we'll see why that happens in this example, right? So part A, it uses 500 watts of power. What is the resistance of the coil? Well, you can find that the resistance of the coil of the air purifier, it doesn't change, it's fixed. It depends on the material it was made. Right? That is not a problem at all. But if you use that resistance and you stick it into a 240 volt RMS electrical supply, how much power are you giving it? So the power consumed, or rather going through that coil, was 240 volts square divided by its resistance, which gives you this value, which is easily almost 5 times more than what it was designed to do. Right? It was designed to be 500 watts of power only. So should it break down? Yes, it will. Right? You will learn about safe power maximum current rating, right, in your CT ones. Right? So this obviously won't work. Okay. Which is also explains why my air purifier didn't work. Not mine, my cousin's air purifier didn't work. Alright, this is just for fun. Right, so the lesson you should learn from today is to learn physics and save money. Right, this advice will save you at least $20 and above, right? Because if you don't attend this lecture, your friends who don't take physics or were not here, they don't remember, they go and buy something off Amazon, didn't check the power reading, plug it in, boom, it goes away. All right, and hopefully it's not something a big explosion. Right, number 6. One more example to familiarize you with the root mean square current of AC. This is what you get in a typical exam question, right? They give you the equation, they give you the resistor, ask you to find all this. Okay? So first we must be able to understand what this means. Sine omega t means it's a sinusoidal wave. 9, that would be the maximum current. Right? Once you have that, it's not difficult. Right? Once you have that, you're asked to find the root mean square current. You know the maximum, you know the equation. So equation very, very useful. Imagine you don't know the equation, you got to do root mean square by squaring, meaning, then rooting it back. Wow, very difficult. Alright, for sinusoidal wave, just apply the formula straight away. Right, knowing the background, right, knowing how you got it, it's easy to just directly apply it and have your answer. Root mean square voltage also very simple. Right, once you have the concept, you have the idea to apply, you get the answer. Okay, any questions? Nope. All right. Part B, they ask for the maximum power generated in the resistor. So you have to be very careful. In AC, the powers they ask you could be average power, maximum power. It could be power at a certain instant in time. Okay, so you have to be careful what they're looking at. So here they're asking for maximum. Maximum easy, right? I square R, done. I naught square R, sorry. Right, which means the maximum current squared times R. Next, they ask for the average power. So you learned just now, right? Average power is just I square R, or root mean square current squared times R, or the mean square current times R. I say again, mean square current is here. Look where my cursor is. Root mean square current is here. Right, so it's either the mean square current times R or the root mean square current squared times R. Right? I had to practice this a few times. And you get this. So at this point, I ask you, is this the correct way to do it? Is this the correct way to find the average power? The answer is, if this question was given to you straight away, right, without part A, part B, yes. Yes, you can use this method to find. But if you have already done part B, isn't there a simpler way? Isn't there a simpler way? There is a simpler way. So save your brain power. You need it to solve EMI and all the other topics, right? So quantum physics later on. Right, so use this. Right? If you have already solved for the maximum power, don't waste your brain power again and resolve this. Just take this divided by 2. Okay, this is accepted. But once again, what is a clause? Only for what wave? Only for? Very good. Only for sinusoidal. Last one, they ask, sketch a graph to show how the power dissipated P varies with time, assuming omega is 100 pi. Omega being angular frequency here, right? In case you don't know what omega is. So first, power dissipated is given by P equals to I square R, this equation, which means you end up with P equals to 972 sine squared omega t. If you have been in my last lecture, you know how to draw this curve. It was a sine square graph with 972 as the maximum, right? So next, you need to determine how long is the period. Omega is 100 pi, but you know that omega is also 2 pi over t, which gives you t equals to 0.2 seconds. Okay, so break it down step by step. Once you have that, draw the graph, easy. Sine square graph, draw this. Remember the bottom is curved, not pointed. Maximum, dot it out, label it clearly. Right? Label the y-axis, label the x-axis with seconds. Right? And you also clearly know where the average power is. Okay. Done. Right? Done. Any questions? So by end of this exercise, this page, you need to know the root mean square current, how to find for square waves, how to find the average power for square waves, then how to find the average power and the root mean square current for sinusoidal waves. Okay? That's what we have done until now. This is a summary given for you. It's at the end of the page, so you see there's something missing, right? Which explains why the lecture is still going on. We are moving on to the last two, right? The last two segments. Last two segments are important because it involves you in your everyday life. How many of you knows about transformers? I know them, right? Yeah. I grew up with transformers, but my transformers not so shiny, not like yours. Your transformers are super shiny and can talk. My transformers are the plasticky kind, then you transform. Yours is the movie kind. Okay? But I'm not talking about this kind of transformers. I'm talking about this kind of transformers. So interesting. Right? How many of you have seen this kind of transformers? How many of you have seen this kind of transformers? How many of you? Wow, you're very good at you all to keep raising your hand. Next time you all must sit in front. Give you all more attention. Very good. How many of you have transformers? Not the toy. How many of you have transformers? How many of you have a phone? How many of you have done a charger? Do you know your charger has a transformer? Do you know that the power brick that you have a transformer? Exactly, right? So transformers are in your everyday life, and it is all thanks to one person, right? It's thanks to Mr. Tesla. Right? So what is the use of transformers for? Remember at the start, I told you that the power generated in the power stations are in AC. It's in AC. When it's in AC and it's transmitted over the power cables, right? I mean, whether it's AC or DC, or transfer over the power cables, there will be power losses because of I squared R. Because of I squared R. Okay? The current through the cable times the resistance of the cable will make you have power loss. Now, how many of you know that oil prices are high? Yes. Okay, so all my questions you all should know. I see you all don't raise an eye, so don't ask me. I just ask rhetorically. How many since you all know that oil prices are high, do you know that the natural gas we burn, the coal we burn to create electricity, costs money too? Right. So imagine this: if you send the electricity through the cable and it's going to lose energy, are you losing money? Right? You're losing money, but when you lose electricity, you don't feel the pain, but when you lose money, you feel the pain. But actually, it's the same thing. It's the same thing, right? Right? So you don't want to send it at a very high current. Do you agree? You look at the power loss equation. You don't want to lose it, send it at a very high current. You send it at a very high current, you lose money. So what can you do? Can you decrease the R? Can you decrease the R? Yeah, you can, right? But how do you decrease the R? R equals to rho L over A. You can either shorten the length, that means your house, your beautiful house, is next to a power station with smoke coming out. Cannot be, right? Or next to a nuclear power plant, worse if you have a nuclear power plant. Whoa, everybody stay next to a nuclear power plant. All radiate green next time. Cannot be. Can you make the R equals to rho L over A? Can you make A very thick? You have a very thick copper wire. Can or not? If only you have infinite amount of copper. But you don't. Copper costs money. Copper is also very, very expensive. So what do? You want to decrease the current. You want to decrease the current. And having a transformer allows you to do that. Okay, later I'll tell you how. Right? But I'm going to tell you that first the purpose is to, at the generator, it creates it with a certain current. What you do is you step it up. Once you step it up, the current becomes very, very, very small in the wires. Right? But current very small, voltage is very, 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 very high. It's not useful for your 12-volt computer. It's not useful for your 12-volt handphone or 9 volts. Cannot, so you need to step it back down. All right, step it back down to 240 for a refrigerator, for a TV. Okay. So in reality, this is where it would be. This is the power plant. This looks weirdly like a nuclear-looking one. The step-up transformer is here. Step it up, and you have this, what you call the pylons. How many of you have seen this before? The pylons? Right, very good. Why am I asking you a question? Okay. But thanks for all the hands raised up. Thank you. Right, you have seen this. Good for you. Where is this in Singapore? How come Singapore don't have high voltage transmission lines? Where are they? Underground. Wow, you all are very good. Yes, it's underground. So every time you see the roadworks, them digging out the ground, it's them either laying one more cable, fiber, water, everything is underground. So Singapore is very beautiful. Right, you have all these high transmission cables. You don't fear that one day you will break, fall into your car, and you. So transform through the power lines. Right before you use for you, they cover it down for you to use at your home. All thanks to Mr. Tesla. But we are using it today, like nobody's business, right? Like, oh yeah, it's always like that. But do you know that when they tried to do it at that time, he had an enemy? You all learn about Edison. Who is Mr. Edison? Edison is also a great guy, right? When I was young, my mom taught me about perseverance. He said Edison tried 999 ways to create light bulb and he failed. And he said, I've only found 999 ways that it doesn't work. The next time it will work, right? Well, that's just a nice story, but when you grow older, you know that it's a fairy tale, right? Edison is a scientist, but he's also a manager, businessman. He championed DC circuits. And he had a lot of clout. He had a lot of political power, right? Scientifically, he had a lot of clout. A lot of people believe in him. So he championed this, whereas Tesla championed the other one, right? He championed the DC, Tesla championed the AC. But because he had a lot of power, the pun not intended. Because he had a lot of power, Tesla couldn't take this off, In his lifetime, he couldn't. So sad. Right? But history has shown which is the better one, right? DC circuits, you need very thick copper wires. You need to have a generating plant 2K within your house. Then you may smoke floating over. Whereas Tesla's one, you can let it be very, very far away. No problem. Your wires can be very thin, can be thin enough. No problem. So history has shown who has won. So do you own a transformer? Yes, these are all your transformers. Right? In the diagrams that I'll show later on, it will all look like this. Right? This is what the circuit looks like. But in reality, the coils are not on opposite ends of the donut. It's on the same end, right? It's on the same end. For engineering purposes and for some other issues I'll raise later on. Okay. So number 7. A nuclear power station, wow, scary. 2 million watts of electrical power is transmitting this electrical energy through cables which have a total resistance of 5 ohms. Find the power loss in the transmission cables if the input voltage is stepped up to 500 kilovolts. How do you do that? Okay. So if this is the power generated, if you step up the voltage, the current will go down. Okay. This is the current that will flow from the power station through your home and up again. Okay? Once you found the current in the cables, you use I square R and find 80 watts. At this point in time, I want to highlight this. For power losses, especially for this kind of AC question, can I recommend this? For power loss, always use I square R. Can you write it down somewhere? For power loss, always use I square R. Why? Why? A lot of students ask me, why cannot use V square over R? Can. But take out a calculator and try. If you use V square over R, a lot of the students use 500 kilovolts square divided by R. A lot of my students use 500 kilovolts divided by R. And what do you get? You get a very, very, very big number. Anyone trying it yet? 500 kilovolts divided by R, what do you get? Anyone? Shout it out. 1, 2, 3, 4. Sorry? 5 times 10 to the power of 10 is 5 times 10 to the power of 10, 80 watts. No, Mr. Ho, cannot be. I just proved physics is wrong. P equals to I square R is 80 watts. P equals to V square over R, not the same answer. Physics must have failed. No, it's not physics has failed. It's because the V you use is wrong. The V you need to use is the V across the cable. But it is something that I've seen repeatedly again and again. Even after I give this lecture, I've seen when I don't give, well, it happens super often. I give this part in lecture, I stress it, it becomes less. So write it down, right? The V, if you want to use V, is the V across the cable, not at the start. Can? Or? Right. So next they ask you for the output at the destination. So at the destination there's an output of 499,980 volts because 20 is consumed within the wires. Okay. Part D, if you didn't step it up enough, if you only step it up to 5K volts, which is still pretty high, but not high enough, you have a current of 400 amperes, you have a power loss of 800,000 watts. So like I said, let's say 1 watt is $1. Let's say 1 watt is $1. Would you rather waste $80 transmitting the energy, or would you rather waste $800,000 transmitting energy? Which one will you choose? Obviously, that's a rhetorical question, right? And this is all thanks to the engineers and scientists who have worked silently in the background to create this, right? If not, imagine, can you imagine you pay your electricity bill, you go home today and tell mom and dad, if there are no engineers and scientists who, it says, so Mr. Tesla, our electrical bills will be 10,000 times higher. You see what your mom and dad will say. You will have no TV, no handphone, no refrigerator, everything no electricity, because it will be too expensive. Or your electricity bill will be 10,000 times higher. It's more than I think than your yearly salary. Oh, cannot be done. Right? Good. Next, example number 8. This is to hit home the idea that the I square R, right, is to hit home the idea that stepping it up to a higher voltage helps you lose less power. So P equals to VI, I equals to P over V. The power loss in the cable is I square R, fine. Right, but they want to show that the P is proportional to V. Now listen carefully, this V, again, my friends, is not the V across the cable. This V is which V? This V is the V of how high you step up the voltage. Okay, it's how high you step up the voltage. Okay? And it can only be as high, and this is the power, the higher you step up the voltage, the lower the current will be. Sub this into this equation, there you go. Sub this in this, you get the power loss is proportional to 1 over V squared, done. Okay? Which explains why we want to step up the voltage as much as possible. Any questions? No question? Not curious? Isn't that a very obvious problem why they didn't address? If I can step it up more, I can reduce the power supply. You should be asking me right now, Mr. Ho, why we don't step up the voltage to infinite? Or 99999999999999999999999999999999999999999999999999999999999. Why? Why not? Why not? No, it's not expensive. Yes, dangerous. Why? Very good. Why is it dangerous? Have you seen those symbols? Extremely high voltage, be careful. You have never seen before? Of course not lah. Right? Most of us wouldn't have seen it, but if you actually go near to like a sub-power plant, you actually will see it, right? But why is it dangerous? Why is it dangerous? Have you seen lightning? Have you heard thunder? Yes. What is lightning? Lightning is discharge of electricity when the potential difference across the air is too high. Which means if I put the voltage at 9999999, it will discharge through the air. Bzzz, bzzz. Also cannot be. Which is why we leave it at a certain value high enough to save money, but not so high to fry every person that walks close. Can? Huh? So this is science, right? Science. We know how it should be, but we also know realistically how it can be. Done. Right. So today I want to show you now what and how it actually really works. Okay, how it actually really works. I've got 20 minutes. So this is what it looks like in your diagram. What you have in the middle is what you call iron donut, right? It's mostly made of ferrous materials. It's in a donut shape, right? Square, donut, whatever. As long as there's a hole in the middle, it's fine. So this is what it's going to do. This is the overview. You have a whole chunk of words there, correct? I'm going to show you how it works in this slide. First, an alternating voltage is applied here. Is it because you have learned this in secondary school already? How many of you have learned this in secondary school? But do you have all these symbols like flux? No. Then listen. Okay. First, so you must listen to a story because you must know then where the problem can be wrong. Okay. First, you have an alternating voltage here. It causes an alternating current to flow. Now you all know what alternating current is. So when your current goes this way, your flux is pointing up. When your current goes the other way, your flux is pointing down. So you have a changing flux on the left-hand side of the donut. This flux, because this is a complete donut and it's ferrous, the flux, the magnetic field will be, or magnetic flux will be transmitted over to this side. Right? So between on the right-hand side, there's also a changing magnetic flux, up and down, up and down, up and down, up and down. And where do you learn? There's something that you learned in the previous chapter. What do you learn? When you have a changing magnetic flux and you have coils, you have a changing magnetic flux linkage. And by which law? 1, 2, 3. Faraday's law induces an alternating voltage in the secondary coil. Just like the answer, all different answer. It's Faraday's law. Either that or at different times, my old ears cannot hear them properly. Anyway, there's an alternating voltage. And if the circuit is not complete, then there will be induced current and it will be an alternating current. Okay? Thus, and this is an important point, this is a circuit for transmission of electrical power. We always use an ideal transformer, meaning the power here on the left-hand side must be equal to the power on the right-hand side. That is what we assume. Okay? And hence, we can then step down or step up this transformer depending on the number of coils. Chim know this one. This is NX, but I'm going to just explain it once. Okay, just explain it once. Important, for your understanding. So here, the voltage applied, some of the voltage will be consumed in the wires under I, R. The rest will become the EMF here in the coils. Then this is transmitted over to this side, depending on how you step up or down. This is transmitted to this side under ES. And this ES is the EMF on this point, on the secondary side. Some power loss in these cables, and this is what you have across the device at the end. Now, you know the EMF is number of coils times the rate of change of flux. You know, the EMF is the number of coils and the rate of change of flux on this side also. Since the flux is also the same, and if we say that the resistance here are close to 0, right? We can say, is this correct? Wait, this is the what I just said, sorry. Right, the EMF, EP here, is given by this. If the currents are 0, if the resistance are 0 in the primary circuit, VP equals to EP, which equals to this. So just look at the left hand side again. You have the incoming voltage. The EP becomes this, and IR. If the resistance is 0, your VP is approximately equals to N d phi dt. Okay? The E side becomes this because of your Faraday's law. VP becomes this because this becomes 0. Same thing on the right hand side. There are, however, some assumptions. We assume no flux leakage. That means the magnetic fields, the magnetic field lines doesn't escape. It stays within the donut. All right. Just now I said, why are the coils over one another instead of on both ends? Because when they are over one another, it reduces the loss of flux. If there's no load, then ES equals to this. Then which means that since the flux are also the same, both of them are the same, you can then put VP and VS as related to NP over NS. So in secondary school, you learned this as an equation. What I show you is how to get there. Saw the difference? Right? This part is okay, no load, if load is easy. Right? This is the difference. This flux will be the same. This will be equal to this. Hence, you have this, hence you have this. Okay? But there are a lot of assumptions, listen up, there are a lot of assumptions leading to this. The first assumption is what? Ideal. Ideal. Right? And it's only ideal only if there's no energy loss, no heat loss, no magnetic flux loss, so on and so forth. Okay? Oof. This part you already know in secondary school, so I'm just going to very quickly skip through. Turns ratio. Right. I want to highlight this also. Turns ratio. You want to learn in secondary school about turns ratio? Yes or no? Did they have a specific way of saying which one over which one is a turns ratio? But there is. If you look across textbooks, which I did, right? Most textbooks, I don't say all, but most textbooks put turns ratio as VS over VP. That means in the exam, I can tell you the turns ratio is 5,000. You need to know that it means that the secondary side has 5,000 turns to 1 turn on the left-hand side, on the primary side. Because I got students saw the word turns ratio, cannot change it to this ratio. You thought it's 5,000 on the primary side and 1,000 on the secondary side, and wrong. So that's something that's not in the textbook. I mean, not explicitly stated. Next, you say it's an ideal transformer. So input power, primary side, is equal to secondary power on the secondary side. Since they are the same, you can rearrange to be like that. So here, VS over VP is inversely proportional to IP over IS, which combining both gives you this simple equation. So if you were lost by every single thing I said just now, today, I mean from the transformer side, you have to remember this equation. If you just can only remember one thing in 1 hour, this is the one thing I want you to remember. Okay, which most of you should have already remembered. Wow, thirsty. Right. Let's try. Example, 10 lamps rated 24 volts, 24 watts, 12 volts connected in parallel of the mains of 240 volts. Find the turns ratio of transformer needed. I mean, without looking at your paper, look at the screen, how would you solve this? What's the first thing you will do? Write down the equation. Turns ratio is this. Right? So which is the secondary side? The side where you're using the things is usually the secondary side. The side where the voltage coming is usually the primary side. Sum in the numbers, done. Booms. Answer 1 to 20. Easy. Very easy. Next, what will the current drawn from the mains if the transformer is 100% efficient? Current per lamp is 2 amperes. You have 10 lamps, so total is 20 amperes. So if 100% efficient, the power in the primary coil, which you don't know, depends on the power in the secondary coil. So 20 times 12 volts, boom. Right? You can find 240 watts as a power. And since the voltage across the primary side is 240 volts, your current is 1 ampere. All right? I hope you are trying to understand the examples here. I know there is also like a practice like in students saying that, okay, never mind, the notes are all there, I'll go home and study. But why don't you try to understand it here? Or I think you should maximize your time. If not, you go home, then you sleep at 1, 2 a.m., then you come back next day, feel tired. So I feel pain that if you are doing this. So I try to make it as simple as possible so that you can understand on the spot. So please maximize your time here. Oh, example 10. Yes, you can see example 10 looks a little bit more not sharp, which means it's a A-level question. Can you cover the solution? Can you cover the solution? Just press yourself, cover the solution and try to figure it out. I give you 3 minutes try. Cover the solution and try to work it out. This MCQ question is quite sneaky. All right. So if you have already tried it, you'll realize that this question is really quite sneaky. Right? They want you to find the average power, but what do they give you? Oh, they never give you the root mean square voltage. They give you the peak voltage. Then you're like, oh no, it's a peak voltage. Then how do I convert to RMS? Then you look at this. Can you see this sign? Very, very small. It says that it's a sinusoidal AC, which then allows you to say, oh, okay, if the peak voltage was 180, so big, if the peak voltage is 180, I can then square root 2 to find the root mean square voltage in the primary side. If you didn't do that, the rest of your workings will be gone. Once you know that, then you use the transformer equation. The turns ratio, NS over NP, is given by 2 to 1. 2 to 1, step down. Okay? Very strange. It's not, sorry, it's a step down transformer. They say it's a step down transformer. So it's 2 turns on the primary side to 1. Very sneaky. It's not a turns ratio. The 2 to 1 they give you is not the turns ratio. It's the ratio 2 on the primary side, 1 on the secondary side, because they say it's a step down transformer. Also, you cannot go in making assumptions that 2 to 1 is a turns ratio. You cannot. So knowing that, you know Vs over Vp is Ns over Np. So you bring Vp up, the root mean square voltage at the primary side over 2 gives you the root mean square voltage on the secondary side. This is how you should read it. VRMS, comma S, S means secondary side, which is on the circuit side. Once you have that, then you just use your favorite equation, V equals IR. You know the V, you know the R, you find the I. Very okay. Once you have that, I square R. The current through the 40 and the 80 ohms are the same. I square R, you get 33 watts. Answer, it's B. You did 1, 2, 3, 4 calculations to get one answer. It is a challenging MCQ. 4 calculations for one answer. If some of you have faster ways, please let me know right after this lecture. Right, so what did I do this lecture? Let's recap. What did I do this lecture? Right, what did I do? I covered part C and D. I started part E, right? And I covered all of part E for you. I showed you that the root mean square current for a sinusoidal wave is given by this equation. I showed you how to get this equation, right? And this equation is only true for an ideal transformer. So next lesson, what am I going to show you? I'm going to show you an extension of part E, E star, right? The power losses in a transformer when it's not ideal. While it is not something that Cambridge tests you with an equation, it's something that Cambridge can ask you in the design of a transformer. Okay? Then I will then end off with the part F next lesson. Please prepare your tutorials because I would have around 20 minutes left after the lecture, and I've promised the teachers to begin the tutorial. If not, you have too much thing to do in the tutorial time, cannot finish, right? So bring your tutorials, do questions 1, 2, and 3. Okay? Questions 1, 2, and 3 at least. All right, thank you very much. Bye-bye.